Okay, welcome into our second video on regression. In the last video, we introduced what regression sort of means. We're trying to learn a relationship between x and y that allows us to predict values of y given values of x. And we're basically trying to figure out this alpha and beta such that we have kind of our line of best fit. And we close by saying, what does it mean to have a line of best fit? You can sort of visually see you want the points to go, or you want the line to go through the points of data, but we need to really quantify that in mathematical terms to make sure we're consistent and concise. So first of all, the kind of central concept between fitting a line is thinking about error. And here, like this line of best fit, these are our predictions for y given different values of x. So if I have the x value here, my prediction for y would be this value because it's on my kind of line of best fit. If I plugged in this x value here, it would spit out this value of y, which is the value on the line. So for the actual data points, we have a predicted value, and then the predicted value, the distance from the actual point, is the error. What do I mean by that? You can see this data point here. This is an actual data point in the data. And our model for this x value would have predicted this data point. And I should have different colors, I just don't have different color markers, but you can sort of see the idea. This real data point, what our model predicts for that data point, and this distance is the error. We overestimated that data point, the data point given our x value, and this distance between those is our error. For this data point, we underestimated, right? So given this like x value, this is the y value that we would have estimated, and clearly we underestimated what that true data point was, and here's kind of the error in that sense. So you can think about each of these points having an error, some bigger, some smaller, versus the line of best fit. We can actually write that error down. We can write that as yi. We're going to be using index sub I for the rest of these calculations. That's just saying like y1 is the first y value, y2 is the second y value, etc. from 1 to n. Our error is going to be yi minus alpha minus beta xi, and again xi is the I value. And this kind of makes sense because this is negative alpha plus beta xi. It's the negative of this side because this alpha plus beta x is our predicted y. Remember, y with a hat is a predicted y. So the error is the actual value of y minus the predicted value of y. That's our error. Now you're probably thinking, okay, well some errors are going to be some errors are going to be positive, some errors are going to be negative. So what if they cancel out? And what we're going to do is we're going to square it. So that ensures that the error is always positive. It's adding up, so we don't get like errors canceling out. You might be thinking, why don't we use absolute value? And the idea here is that squaring it will punish big errors. So, everyone's familiar with the square function. It's, the y value exponentially grows as the x value gets bigger. So the bigger the error you get, the more punishment that the error will be, which is why we have the square. We want to minimize like really, really big errors. And what we're going to do is to find the total error of the line of best fit, we're going to sum all over all I. So from I equals 1 to n. This is just the sum of signs. This means we do y1 minus alpha minus beta x1 squared plus y2 minus alpha minus beta x2 squared plus plus yn minus alpha minus beta xn squared. And that's our total error. And what we want to do is minimize that error. And the way we write this is we say we want to choose alpha and beta such that we minimize the sum of our squared error. So this is how we figure out our line. We choose the alpha and beta that minimizes that square error, and that's a concise mathematical result, and it kind of makes sense. We talked about you have positive error, you punish the big errors. I'm saying error so much that it's losing semantic meaning to me, but hopefully not to you. And choosing alpha and beta like that will, in that sense, will give us the relationship we want. So this is a formal mathematical statement, but what we want to do now is actually find alpha and beta. And you can imagine, you could tell a computer to look over all combinations of alpha and beta, each time try different alpha, try different beta, see what the error is, and look over the whole space and pick the alpha and beta that minimizes this term. That's fine. Might be computationally intensive. It's a big space. So let's actually just try to solve it with pen and paper, or marker and whiteboard, try to solve it analytically, get a result in terms of the data x and y. And the way we do that, if you're familiar with minimizing or maximizing, I mean, you can imagine this is univariate. We're optimizing over 2 parameters, but you can imagine you have some like weird function that you're trying to, what we're trying to minimize. Let me draw it the other way. You have some, weird function that you're trying to minimize, and at the minimum point, the derivative is going to be 0. And we're not going to get into like a ton of the math here, but there's a bunch of conditions that need to be satisfied for it to be global minimum, whatever. Just trust me on this point. This is more on the regression stuff instead of the math stuff. To find the alpha and beta that minimize this term, we want to take the derivatives and set it equal to 0 and solve. So let's go ahead and take the derivatives. I'm going to call this whole thing z, just so I can like write the partial in terms of something. I'm kind of crooked. That's okay. Here, let me write this over here. Straighten it out a bit. Okay. So my first derivative is going to be the partial of z with respect to alpha, and this is a classic chain rule problem, right? First of all, this is a sum, so it might be weird to think about taking a derivative in terms of sums. But remember, the derivative of a sum is just the sum of the derivatives of each term. So we don't have to work. We're just deriving each term and adding the derivatives together. And then each term, is the same structure, and it's just the chain rule. We have this function of alpha, and then it's squared. So first we take the derivative of the inside. That's negative. So negative, and put it outside the sum. This is a useful trick that's going to come in handy a lot when you have like a scalar. So this is -1. You distribute it outside the sum, because essentially you're doing just like 2a plus 2b. This is a sum. Each term has a scalar equals 2a plus b. That's what we're doing here with -1. Okay, so that's good. And then so that's the sum of the inside with respect to alpha. And then we have to take down the 2, right? So it becomes -2. And then this exponent just becomes 1. So then we have that. We want to set the derivative equal to 0. And it's a very similar derivative for with respect to beta, -2, because the top comes down. The derivative with respect to beta of the inside is -xi. I can't take the xi out of the sum because it varies with I. So xi yi minus alpha minus beta equals 0. Awesome. So this doesn't look like we really did anything, but we have the roadmap for the rest of our problem. We have 2 equations, we have 2 unknowns, and now we need to solve the system of equations to get alpha and beta. So in this video, we're going to start by doing the alpha part. I'll do it on this side. So I want to set this equal to 0, I'm setting it equal to 0, and I want to solve for alpha. I want to isolate alpha. First off, I can just divide each side by -2 because 0 divided by -2 is 0. So I get the very nice I equals 1 to n yi minus alpha minus beta xi equals 0. Okay, and in this video and the next video especially, we're going to be doing a lot of sum math. That sounded like a weird sum, S-U-M, so summation math. Here, we're just adding a bunch of terms. The sum term is outside of the parenthesis. I'm going to bring the sum into the parenthesis and basically I apply the sum to each term, which is fine because in the end, we're just adding up a bunch of terms. It doesn't matter if, I write it this way. So I'm going to write, and I'm going to stop writing I equals 1 to n just to save time, but each sum is from 1 to n. So the sum of yi, put the parentheses, so the sum just applies to yi, minus the sum of alpha, minus the sum of beta xi equals 0. Okay. Doesn't look like we did much, but what's really cool is that we're summing something, alpha, that doesn't depend on I. It doesn't index with I. So like if I summed 4 from I equals 1 to n, that's just saying 4 plus 4 plus ... plus 4 n times. And that just equals 4n. Because the 4 doesn't change with n. And that's the same with alpha. The alpha doesn't change with n. We also have beta, which is, again, we saw before, it's a scalar. It doesn't change with I, so we can take it out of the sum. And we're going to get sum of yi minus n alpha. So just, summing alpha 1 to n alpha minus sum of beta. Sorry, I want to take the beta outside the sum. minus beta sum of x equals 0. Okay, so that looks a lot better. I now have something just in terms of alpha and 0, and I'm going to put the alpha on that side, divide everything by n, and I get sum of yi minus beta, I should keep with the parentheses, keep it consistent, minus beta sum of xi all over n equals alpha. So now we've isolated alpha, and now we're dividing both sides by n. What is the sum of y divided by n? That's just the mean of y, the average of y. Add up all the values, divide by n, and you get the mean. So we're going to write that y bar, which is the notation for the mean of y. Let me write that better. Y bar minus beta, and then the sum of xi divided by n is also x bar. So x bar equals alpha. Boom. Awesome. So we did it. We solved for alpha. In this in our result. Unfortunately, and this is kind of intuitive. Like if you just look at our line of best fit, if you solve this for alpha, so it's going to be y hat minus beta x equals alpha. We're just plugging in the average of x and y for y and x here. So it kind of makes sense. You're averaging over the data. The issue is we have alpha in terms of beta, and we want to get alpha and beta just in terms of x and y, right? Because we want to be able to calculate them from the data. So it's not enough. We're not done, but we have alpha in terms of beta. In the next video, we're going to finish the calculation and solve this partial derivative of beta and use this fact to get the full result. So we'll see you next time.